All right, uniform circular motion, my favorite topic in physics. So this is 1.1.3, I think, 1.3, uniform circular motion. Now, what this word it means is that an object traveling in circular motion, obviously, uh, with the same speed, right? Same direction, same speed, no changing of anything. Now, first question, when a thing is in uniform circular motion, what direction is the acceleration? Now, what you might be thinking is, well, since it's traveling with the same velocity, with the same speed, right? Around the circle with the same speed, there's no acceleration. Well, there's no acceleration. But no, that's not true. When you think about it, if there's no acceleration causing change in velocity, what would the object do? The object would travel in a straight line like that because there's no force applied to it. There's no acceleration. There's no change in the velocity, the direction it's going. You just travel in a straight line. Now, since the object in this case is traveling in a circular path, something is changing the direction. That means something is changing the velocity. This means a force is being applied, and the force is applied toward the center of the circle of the path, the circle path. So let's get rid of that center. And we can think about it in two ways, right? Just think of anything that travels in a uniform circular path. It could be you are throwing a hammer, hammer throwing. You are a hammer throwing athlete, and you spin this hammer around you with you at the center of its uniform circular motion, right? What is causing that hammer to stay with you instead of it flying straight into the air? Well, in this case, it's the tension of the string that's holding the hammer um, to you, right? The hammer is held by a string between you and it, and the tension is causing the acceleration. Okay, let's say a car is traveling around the circle. The car is traveling around the circle. What's causing the centripetal acceleration? By the way, that's what we call this acceleration toward the center, centripetal acceleration. Well, in that case, the friction on the tires would be causing the centripetal acceleration. And we can visualize this acceleration toward the center in another way. So in this case, we're drawing the velocity of the object. So when the object is over here, on that side of the circle, its velocity is going this way to the right. And when it's over here, it's going down. And what we want to figure out is the change in the change in velocity. We back. So the velocity. This here is the final velocity, and that there is the initial velocity. What we want to find out is the change in velocity. Pretty simple. Change in velocity. You have this triangle. Change in velocity is final minus initial. Now what we do here is we draw the final as a vector and we draw the initial as a vector and we draw them and we write this out. And the next thing we do is we change the direction of this vector and flip this to a plus. So now it's easier to visualize it. And the next thing we do is we simply add the vectors together. Pretty simple, head to tail, like that. And then you connect the end. So you connect this. Now, if you do this properly, like on paper, using rulers and proper angle, you get a vector that's pointing directly towards the center. Now, you can see from this one here that it's roughly pointing toward the center of this circle. So now we realize that the acceleration of an object in uniform circular motion is always towards the center. Now, bringing back to the car example, so the car going around the circle example. So in that one, suppose we have a car, just traveling on flat road. What's causing the centripetal acceleration in this case is its friction, the friction of its tires. But we see in many like racing events where the racetrack is made slanted on an angle. So now the car is traveling on an angle, and why is this? Because when let's say when the car is traveling on flat road, its normal force is perpendicular to the ground. It's just going upwards, 90 degrees. But when you have a car traveling on a tilted road, its normal force will be tilted. It will also be tilted, but still perpendicular to the ground. So now let's say the center of the circle is this way, right? If the car is tilted like this, some of its normal force is going towards the center. Now in physics, we say this as the normal force has some horizontal component of acceleration toward the center. Thus, this provides some centripetal acceleration. Now, what this means is to go around the same curve, right? The same curve, same size. The car relies less on its friction. So at some point, the car can just go along the curve without using friction at all if you find the right angle for the road tilt. But anyway, that's everything about bank curve. So this is called bank curve in this unit. Next thing is Kepler's planetary laws. Kepler. Too long, can't be bothered to write it down. So this guy has 3 laws, and they are pretty useful. Used by NASA probably. The first law is any planet orbits around the sun, around a star, orbits in a. Sorry, let me restate that. Any planet orbits in a oval, circular orbit with the sun as one focus. So there are 2 foci. Sun as one focus, another focus. Now this is the planet. Simple as that. So now we have the diagram for the first law. Let's go to the second one, which is the planet sweeps equal amount of area from the sun to its location in equal amount of time. So what this means is if I draw an area out from here to here, what this means is, let's say the time is the first month, right? Let's say we have Earth over here, and that's the second month. Earth is over here, right? So you travel this much distance, and the area it covered is swept is this much area, that much area I just drew. Okay. Now, for example, now we are in June, July. Now the area it has swept will be this much because the area swept in equal time will be the same. What you see here is an interesting thing is that when Earth is further away from the sun, it travels at a slower speed. But when it's closer to the sun, it travels at an incredible, like way faster speed than when it's further away. Now, this is another way of explaining the second law of Kepler's planetary motion, is saying when it's further away, slower, closer, faster. But what we say usually is just sweeps equal amount of area in equal amount of time. And the third one is really straightforward, is a planet's period depends on the radius of its orbit. This is really simple because we see this every day, man. Not every day, but you get the example. So at the center, we have the sun. And now this is the orbit of Venus, which is closest to the sun. And we have the orbit of the Earth. of Earth, which is further away. Now, as we can see, the orbit of Venus is much shorter. Therefore, the period of its orbit is also much shorter. So a year on Venus will be very short, whereas a year on Earth is 365 days. And we know on other planets which are further away from the Sun, it will take even longer to finish one revolution around the Sun. Therefore, it will have longer periods. For example, Saturn will have very long period, 26 years or something. So that's all the Kepler's planetary laws. That's everything in Unit 1.3, uniform circular motion. We learn about bend curve, centripetal acceleration, and some space stuff. They're pretty fun to do. Anyway, that's it. That's all. Thank you.